Ladies and gentlemen, I'm Darling. I'm glad to share our research on cardiac sound monitoring for assessing prosthetic valve degradation after transapical transgathered aortic valve implantation. Our teams from Chengdu Medical College and Zhengzhou University. This research gives a new way to check valve degradation. The presentation will briefly cover the background, a literature review, key technology for data analysis results, and a concluding summary with future outlook. Let's start with the background. Cardiovascular disease poses a huge global health challenge. The World Health Organization reports that around 17.9 million people die from CVD globally each year, and this death toll is rising. Data from the global burden of the disease shows that the mortality rate of popular disease soared by 68%. A Nature publication also points out that 23% of transgathered aortic valve implantation failures stems from the delayed detection of valve degradation. This data makes it crystal clear how significant CVD is worldwide. Just focus on the images on the right. They illustrate the calcification degree of patients with valvular stenosis over 1 year. We can see from parameters like peak velocity, mean gradient, and calcific volumes that the stenosis degree in these patients have risen sharply. Meanwhile, evidence from circulation reveals that 62% of medical centers lack a long-term monitoring plan. Additionally, traditional detection techniques rely on TTE and CT, cost over 500 per session and can't provide high-frequency monitoring. Or then when the native aortic valve is severely damaged or degraded, these artificial valves are used to replace it. The mechanical valve is made of synthetic materials and is very durable, while the surgical valve is often derived from animal tissues and may have a more natural function but the limited lifespan. We've got a really important point. Heart sound auscultation is still a super crucial part of monitoring prosthetic valve. Now, the core mechanism here is all about this residue at the height that sticks around after cross-linking. This might seem a bit technical, but it's really the starting point of the whole chain of events. That chain is what we call the pathology cascade. So it all begins with immune activation, which then leads to chronic inflammation. From there, things get worse. We see cellular death happening, and that makes the loss of tissue or nucleation kicks in, and we get progressive mineralization and the end of results left flat stiffening and tearing, which ultimately cause the valve to fail. Take a look at the two graphs on the right. As the valve keeps getting calcification deposits over time, it's like adding layers of stiffness and blockage. This calcium deposits build up and makes the valve moving parts less flexible. According to our study design, our study involved 100 TB patients and 100 healthy controls to compare heart sound differences. Using the ETZ-1EC electronic stethoscopes, we collect audio data from mitral, pulmonary, aortic, and tricuspid regions, sampling 31 minutes clips daily for 5 days. We analyze high-resolution multi-point acoustic data via our heart sound analysis to examine duration, intensity, frequency parameter with differential and correlation methods. Let's take a look at one of our key technologies, the audio data analysis tool. The big question is, how does it work? The audio data analysis tool works by first gradually locating the first and the second heart sound to distinguish systolic and diastolic phases in heart sound waveforms, then analyzing parameters like duration, intensity, and frequency to detect valve degradation or cardio issue. After accurately locating the first and the second heart sound, systole and diastole in step 1. The next step, you use MATLAB code to load audio data set variable and calculate parameters including duration, frequency, and so on. After accurately locating the parameters, we integrate this process into an analysis software that systematically streamlines hot sound data analysis from collecting to parameter calculation and results visualization for efficient detection of valve degradation and cardio issue. This table showcases the parameter results with export, especially focus on duration and the decibel values related to the cardio cycle. We look at the results related to frequency parameters. This table breaks down various frequency features, comparing them between males and females for different phases of cardio cycle. The frequency band is selected based on JACC evidence showing prosthetic valve calcification induced low frequency vibrations predominantly emit energy in this range, making monitoring its energy an effective indicator for detecting early calcification in type B patients. In summary, our project encompasses three key platforms: sound diagnostic platform, heartbeat collection platform, registration of clinical devices. Our project has achieved breakthrough one by establishing a high resolution dynamic heart sound library and showcases an acoustic intelligent diagnosis based sound diagnostic service platform via the site. Voice sounds, cough sounds, heart, lung breathing, snoring, and burbling sounds are collected on these websites. And the technical components like man control, MEMS sensor, and sound pickup system. The results of these reports also include the prediction of valve degradation. This system transforms passive auscultation into quantitative dynamic monitoring using evolving acoustic data for early valve function warnings, reducing reliance on costly imaging and leading a new approach in cardiology acoustic passion with future multi-central validate and regulatory approval. This slide shows a collection of films likely to express your gratitude to the individuals and the group individual in this project. We also thanks following funding edges in funding support, National King Program of China,